All right, folks, this last video of 2.2 is about how to work with systems of objects. So every problem we're going to do is going to have two objects, and you might find problems with more. Those are probably going to be the conceptual ones. I'm not going to do all of the math for this. I'm just going to show you how to set it up. If you wanted to finish these problems on your own, I'm just going to write the answers up here. So the answer to question number 1 is it rounds to 2.3 newtons. If you want a more exact number, 2.29 newtons. And then the second problem, you're looking for the acceleration. The acceleration is 1.09 meters per second squared. So again, I'm not going to finish the problems. If you wanted to finish them to make sure you can get the answer, that's awesome. This box problem, you can pause and read it, has two boxes connected. We're looking for the magnitude of the force between the boxes. So I am going to draw some free body diagrams and analyze them, and I'm going to color code them. So box A has gravity, normal force, and then it has this 8 Newton applied force, and then it has a force due to box B. So that is like what the diagram for box A looks like. It receives that 8 Newton force, and also box B is pushing back on it. Box B, however, it also has gravity. It also has normal. Those forces are not the same as one another. Like these two normal forces are different because the masses of the blocks are different. Now, box B does not get the 8 Newton force. It gets the force from box A. So if you look at these two diagrams, they don't have any horizontal forces in common yet, but what you want to notice is that we're looking for the magnitude of the force between the boxes. These boxes are pushing on one another. Newton's third law says that they have to be pushing with equal and opposite forces. So the force from box B is equal to the force from box A. And that's actually what we're looking to find. I'm going to show you a quick way to solve this problem. I'm going to do it in class. I'm going to show you the more proper, slow way to do it. So we're going to start with, I'm going to color code these, right? I said I was going to do that. So we're going to start with box A. Box A, net force in the x direction equals mass times acceleration in the x direction. Quickly add some forces. 8 newtons minus Fb equals the mass of A times the acceleration. Okay, really important that when you have two objects, you know which mass is which. So we're going to use ma for that. Now we're going to do box B. Box B has a net force in the x direction, but it only has one force. It has the force of box A on it, and then its mass B times acceleration. Now the accelerations have to be the same because these two objects are in contact with one another, and they're not in contact with something like stretchy or that changes size. So the accelerations have to be the same because they're literally like kind of stuck to one another. All right, now I can't do anything yet because, actually I can. I have two unknowns. I know the masses, but I don't know the force of the box, and I don't know the acceleration. I am here to find the magnitude of the force between the boxes. So I am going to work with the acceleration. If I divide both sides by mb, I get that Fa over mb equals acceleration. And that's the key to this problem, is I solve for acceleration and then I'm going to work with it over here. But something else needs to happen. Fa and Fb, we need to know that they are the same. So I'm going to now call that force F. So because of Newton's third law, I know that those forces are the same. And I can just call them something simple, and that will then be my answer. So I take this information and I bring it into this equation. So let's do that now in maybe a third color so we can see that we've combined everything into one. So 8 minus F. Remember, I'm not going to call it FB anymore because it's the same as FA. I'm just going to call it F. That equals MA times F over MB. And so now I need to solve, right? So this is where I'm going to exit here. 8 minus F equals, okay, I can rearrange this. This is going to be 5 over 2 times F, and then you would just need to work with that to find the value. So that's the force between those two boxes. Okay, I didn't mess up. That's great. The next problem is about an Atwood machine. And so, again, I'm not going to finish this one. Atwood machines are things that are really just to like demonstrate physics. And it's the same thing as the previous problem. It just looks like it's not. This structure that I attempted to draw is a stand that has a pulley on it. So this is a pulley. We study with pulleys a lot in physics. It's just a wheel with very little friction. We're going to assume no friction at this point in time. Also, no mass to the pulley. And there's a rope over the pulley, and there's a box at either end of the rope. So our job is going to be to find the acceleration, and I'm going to do that in a lot of the same way that I did the other one. Okay, so gravity and tension are going to be the forces on block A. And then for block B, tension and gravity are also the forces on that. So those are the same forces, but this system is definitely going to move. B is heavier. So we know that B is going to move down and A is going to move up because there's an imbalance in mass. Well, this string determines the axis of motion here. So because A is going to go up is the positive direction for block A. Because B is going to move down, down is the positive direction. I said that wrong. The rope is going to move up on the left-hand side and down on the right-hand side. So local direction matters when you're talking about a string. The string moves up on the left, so up is positive. The string moves down on the right, so down is positive. I'm now going to analyze both of these for net force, and we're going to solve for acceleration. And I'll stop as soon as I think you can handle it from here. So we're going to do box A first. Net force equals mass times acceleration. Net force is tension minus, okay, I'm going to be sneaky here, force of gravity. Well, that's just m times g, so I'm going to say ma times g, and that's equal to ma times acceleration. So I just substituted in the equation for gravity and then the mass of A. For B, I'm going to do the same thing. Net force equals mass times acceleration. This time down is positive. So mb times g is the positive force minus ft equals mb times A. Okay. Now, we have a lot of things here, and I just want to make a note of something. I don't know what the tension is. I don't know what the acceleration is, but MA, MB, and G are all things that I know. So I'm going to attempt to solve for acceleration, and that means that I'm going to work with tension. So I'm going to quickly solve this equation for tension. Ft equals MA times A plus ma times g. So the net force plus the weight of A. Once I've done that, Newton's third law tells me that the tensions are equal and opposite. And so that is going to go here. And so I'm going to write this whole big thing right now down here. mb times g minus ma times A plus ma times g equals mb times A. Okay, this alphabet soup is an expression for Newton's second law that takes into account both objects. There's essentially the net force on each object and in force and in mass times acceleration. So your job at this point in time will be to like plug in numbers and make sure that this works out to the answer that I've stated. And again, in class, I'm going to give you a faster way to solve these problems. Maybe not faster all the time, but something that might be simpler to analyze. And that's it.